Let's take a look at 6.5, which is called special cases of factoring. I put special in quotes because it's really not so special. You're not going to approach it any differently. They still come from the same binomial, two pieces being multiplied together. So we'll start this section as we've done the last three and see what happens special in this case when we multiply these together. And we've already talked about this. I did bring it up in chapter 5, right, that this is a special case of factoring when both of the binomials are identical. They have identical terms, just one's positive and one's negative. Right, if we were to multiply this out, FOIL, right, we'd end up with x squared, x times negative 7x, 7 times x positive 7x, 7 times negative 7, negative 49. So there's nothing special that we had to do in this multiplication. Just the end result is somewhat different because these middle two terms happen to cancel each other out. And that's a direct result of one being positive and one being negative and happening to be identical. So right, we end up with x squared minus 49. And if you remember from chapter 5, I did give this a name. I called it a difference of squares. I promised it would come back up, and here it is. All right, does it affect our process of factoring at all? No, not particularly. Right, if I wanted to factor x squared minus 49, I would think the same way. Right, I'd say, well, do these two terms have a common factor? Certainly not. Nothing in common between x squared and 49. If they don't have something in common, I need to unfoil it. Right, what's particularly nice about a difference of squares, I would say this is probably the easiest type of factoring or unfoiling. Once you identify it as a difference of squares, we know because these middle terms cancel out, I need identical pieces. Right? That doesn't really affect our thought for x squared. X squared, yeah, that's definitely x times x. These are identical first term pieces. Right? We also need identical pieces for 49 because we know the middle two terms have to cancel out. There is nothing in the middle here. And the only way for that to happen is for them to be identical. So 49, you don't have to think about, could it be 49 times 1? Could it be 7 times 7? I guess those are the only options. But you don't have to worry too much about it because you know they have to be identical. So I need 7 times 7, right? This would be a perfect square. X times x is a perfect square. These are identical binomial pieces. We just need one to be positive and one to be negative. It doesn't matter which one is positive or negative. And we've factored it. All right, so there's our thought process. We need to identify first. This is a difference of squares. These are both perfect and the middle term is missing. And once you identify it, identical pieces, one positive, one negative. So let's practice a couple really quick, but there's not much to it once you get the hang of it. Let's practice. If I had x squared minus 36, no common factor, so no GCF, and no middle term. No middle term is a key indicator that this might be a difference of squares. There's only two terms instead of the normal 3 in our trinomials we've been factoring. So no middle term, this has to start identical, x and x. 36, there's lots of factors of 36. 9 times 4, 12 times 3, 18 times 2, right? But in this case, none of those are even possible because it has to be identical. So these are nice. Right? You don't have to worry too much about all the different factors. We know in order for the middle terms to cancel out, we need one positive and one negative. It has to be identical. Something like 9x squared minus 81. Let's not do 81. Let's do 64y squared. Looks a little messier, but is it really? There's two terms. That's a big indicator. There's no middle term. There's an x squared and a y squared, so these would be your end pieces. So it is screaming, I'm a difference of squares. Let's unfoil this and think about it. What two identical factors can I place here and here that would multiply to get 9x squared? Yeah, that's right, it'd have to be 3x and 3x. Right, these are identical and they multiply to get here. 64y squared, what two identical pieces could multiply to get 64y squared? Well, that would have to be 8y and 8y. One positive, one negative, game over. Don't have to worry about signs. You're never going to have both positive. You're never going to have both negative. In order for those middle terms to cancel, one positive, one negative. So, all right, you don't have to worry about signs. You don't have to worry about factors. They have to all be identical. And I think this is one of the easiest situations of factoring. Right? But you can be your own judge, I guess. Let's look at some ways to mix this up and kind of throw you off. But if you boil it down and say, I need identical pieces to get this, identical pieces to multiply to get this, all right, I don't think you're going to run into too much trouble. If I had, let's say, 81 minus y to the 6th. This one looks a whole lot of funky, but it still matches. I mean, it doesn't match up with much we've seen in this section, especially having a power of 6. Right, but that shouldn't throw us off. There's two pieces. There's no middle term. All right, what identical pieces multiply to get 81? 9 times 9. Right, what identical pieces multiply to get us y to the 6th? This might be a little bit more difficult of a question, but if we remember back to the beginning of chapter 5 and our properties of exponents, remember when I multiply, I add exponents. So y to the 3rd times y to the 3rd, those are two identical pieces, and when I multiply them, I add the powers. I get y to the 6th, one positive, one negative, game over. This can work with more obscure terms. MathLab likes to mess with you a little bit here. If I had x squared minus 1 over 25. Definitely haven't seen many problems in this section with any chapter or with any fractions in it. But this is a difference of squares, right? X squared. Right. 1 over 25 you might not think of as a perfect square, but 25 you should. You should think, oh, well, that's 5 times 5. Fractions don't work any differently. If the numerator is a perfect square, and it is, and the denominator is a perfect square, and it is, right, then we can certainly break it apart and say, well, what times itself is 1 over 25? 1 over 5 times 1 over 5. Right? 1 times 1 is 1. 5 times 5 is 25. So when I multiply these two fractions together, I get 1/25. One positive, one negative. Bingo. All right, so don't let fractions throw you off either. They're just trying to make this type of problem look more difficult than it actually is. You could also run into a situation with x squared minus 12y squared. And that certainly looks like a difference of squares. The issue being, if I jump straight into trying to unfoil this, what two identical terms multiply to get 27? I don't see any. Are there any two identical terms that multiply to get 12? No. Oh, that's 3 and 4, 6 and 2. It just doesn't exist. So again, as a reminder, always be wary of a GCF. Right? There is a common factor here between these two terms, although you may not see it immediately. The common factor here is 3. These are both divisible by 3. We can remove a GCF. That'd be 9x squared divided by 3. That'd be 4y squared. And here we have a hidden difference of squares. These are now both perfect square numbers. So remember, the 3 has to stick around, but this piece in here can be unfoiled further. Now I can think of two identical pieces that give me 9x squared. And two identical pieces that give me 4y squared. 2y and 2y. One positive, one negative. And we're good to go. So there's a crash course in difference of squares. Again, always be wary of a common factor, but if there isn't one, and you just see two terms with no middle term, you can jump straight into this unfoiling process and look for identical pieces. All right. There's one other type of problem in this section that they consider special, but I don't consider it. I consider it even less special than a difference of squares. All right, they consider this problem a special case. X squared. Let's see. Also 12x plus 36. If I gave you this problem in section 6.3, right, you would have no problem factoring it. And here, I don't want you to think of it as anything special either. So take a second. Try to factor this on your own with your skill set that you already have. This is not a difference of squares. There's a middle term. 12x, there's nothing in common. So it does need to be unfoiled, but what would you do before? You'd say, I know this has to be x and x. You'd say, well, what factors of 36 do I have? 9 times 4, 12 times 3, 18 times 2, 6 times 6. Well, which of those pairs can help me add up to 12? 6 and 6. It just happens that these are identical pairs as well. So 6 times 6 is 36. But now, if I want this middle term to be a positive 12, positive and positive, I need positive and positive. So there's nothing really special about this. You would approach it the exact same way as section 6.3. You just end up with two identical factors, which you could write a little more concisely. If I'm multiplying the exact same piece by itself, you could write it as x plus 6 squared. I don't think MATLAB's going to care which way you write it. They're both correct. But this is why they would consider this special, because you can combine, or you can consolidate these into x plus 6 squared. Was it special in the sense that we had to think about the problem any differently? No, not at all. Just the way you can write your final answer is different than you would normally write it. Okay, so that's the end of 6.5 though. I don't want to dwell too long on this special case because you wouldn't factor it any differently.